So in terms of inherently interpretable models, we started our discussion about things like shallow trees or like simple linear models or simple rule-based models and so on. In this module, for the next 40 minutes or so, we'll do a quick overview of some of these approaches. So let me start by saying that I am not going to touch on the very basic sort of linear models or regularized linear models with like L1 or L0 or L2 style regressions, regularized regressions, but instead I'm going to start from something like around the year 2014, 2015. Since then there has been more renewed interest in sort of like building inherently interpretable models, exploring newer ways than what we had with respect to previous work in 70s and 80s, right? So what I'm not covering is few things. So just linear models, linear logistic regression, regularizations on top of them, and then decision tree construction using greedy approaches. So those are the things that I'm going to sort of put a pin on and assume some familiarity for all of you, but I'll start from the year 2015 and go over some of the approaches that came since then. Okay, does that sound good? All right, okay, so again, as I was saying, so with the renewed interest recently, a lot of approaches, again, the constructs is probably what I would encourage all of you to take away from some of these discussions. So the people have tried to build several kinds of inherently interpretable models. So one is rule-based models. The other is risk scores, and I'll explain what they are in a little bit. And then there is generalized additive models, which had gained a lot of popularity recently. And then there are prototype-based models. Okay, so let's go over each of these. Oh, and also attention-based models. All right. Okay, so let's go to the first set of approaches, that is the rule-based approaches. And I'm going to first talk about a couple of approaches in this categories before I move on to another one. This approach called Bayesian ruleless was introduced in 2016 by Ben Latham and Cynthia Rudin. And this was basically an approach that is, the output of this approach looks something like this, right? So it's a sequence of if-else-if rules. And this is actually the output that they get with their method as a classifier for stroke prediction, right? So this is basically like they were working with some doctors and healthcare experts to design models that can be used to predict strokes in advance or stroke risk in advance. And the requirement in those settings is that doctors want to precisely see the rules that can be used to sort of employ as they go, in their day-to-day decision making, right? So they didn't want any kind of complex models. They wanted something as simple as this, but also they wanted something accurate, right? So this approach is kind of motivated by that scenario. So what exactly is their approach, right? So their approach is basically proposing a generative model which is designed to produce these kinds of if-else-if lists. And the way they design this generative model is by striking a balance between accuracy, interpretability, and computation. And I'll go into some more details about this approach, but you could look at, or anyone could look at that particular if-else-if list that we saw and say, wait, why are they just not using other similar models? For example, what about decision trees like CAD, C5.0, C4.5? Why are they not using these kinds of models, right? The reason, or at least what the paper argues, is that these kinds of models employ greedy-based approaches. So while greedy methods, as we all know, are efficient, they can often get stuck in local minima, right? So the argument that this paper makes is that it is computationally great, but the resulting solution is not going to be perfect in terms of accuracy or interpretability. So that's why they sort of like put forth that there is a need for new methods to even generate things like ruleless from scratch. Okay. So for those of you who are familiar with Bayesian models, here is what their generative model or their generative process looks like. If you think about it, and for those of you who are not familiar, there's no need to worry too much. All that goes on in generative models or these kinds of Bayesian topic modeling style approaches is that you sort of assume a particular process that generates the data, and then you have a bunch of unknown parameters as you assume this process, and then you work backwards and then try to estimate or learn those unknown parameters using different techniques, right? So that's the basic, intuition or concept behind generative models. So what is this particular generative model trying to do? So essentially the generation process says, first of all, pick a list length. So how many rules are there in the list? We sample that number, and then we basically sample a default rule which will apply for things that no other rule is going to apply for. And then we are going to sample the m different other rules in our if-else-if set of the list. And for each rule, what we do, we basically sample the cardinality of the antecedent, which is the left-hand side of the rule, how many predicates are in the left-hand side of the rule. And then we basically sample the predicates on the left-hand side of the rule, right? So you sample the number and then you sample the predicates, and then of course you sample what should be on the right-hand side of the rule, right? And then the observations will be generated from these sampled rules as, find a rule that actually applies to this instance in the data, and then if no antecedents apply or no rules apply, then you basically give it the default rule. Otherwise, you sort of sample a class label based on that rule that applies to this instance, right? So that's the high level. If we were to sort of think about constructing these rules, that's intuitively how you would think about this kind of a process, okay? So I want to note few things here. So one is the sort of sampling the predicates or the conditions. And when I use the word predicate, I basically just mean, these conditions are the predicates, right? So it's like if transient is basic, or if transient ischemic attack, that's the condition or that's the predicate. Okay. All right. So A here is the set of pre-mined antecedents. So what do I mean by that is, whenever they're trying to sort of pick the left-hand side of the rules, they're actually selecting from a set of candidate left-hand sides that are already available. Okay, so they use some sort of like frequent item set mining for those of you who are familiar with a priori style algorithms. So they kind of use that to sort of determine what are some of the frequently occurring patterns in the data and then try to pick left-hand sides from those. Okay, so there is a candidate set and they try to pick from it. So now, just at a very high level, for this kind of a generative process, they use something called as Metropolis-Hastings algorithm. It's essentially like, for those of you who are familiar with MCMC or Gibbs sampling method, so this is essentially one of those classes of algorithms, and using this, they go back and estimate all the parameters in that generative process that they don't know. Right? So for example, before constructing the list, you don't know what will be the cardinality of the antecedent or the number of predicates of antecedent of some rules, or you don't know how many rules you're picking, right? So, but using this process, they go back and sort of learn those and then build the list. Yes, that's the high level idea. All right. So one of the major sources of practical feasibility here is this set of pre-mined antecedents or pre-mined left-hand sides of these rules. And that basically helps them reduce the model space, because you're essentially searching over those rules only in order to find your final list, right? So if your candidate rule set is small, then you basically have smaller search space to look at, right? So they can control the complexity of the problem through that, right? And as long as this set of pre-mined antecedent list is expressive, you will be able to find an accurate enough decision list. Plus, having that set to be small can also help with like better generalization as well. Right? So you need to choose that set carefully in order to find a good or an accurate decision list with this method. Okay? Any thoughts, questions? All right, okay. So the next approach, which kind of tries to simplify this process a bit more further and also makes it more efficient, and also adds some tweaks on interpretability, which I'll also discuss a bit more in our analysis section, is interpretable decision sets. And this is like an example decision set classifier for disease diagnosis task on a particular data set. Right? So what immediately kind of strikes to you is, instead of if-else-if rules, there is a set of unordered if-then rules here. So that's the main difference in terms of how the rules look like. You would be surprised to know that even just a change in the construct from if-else-if to if-then already changes significantly how people perform certain tasks. For example, and I'm going to talk about this a lot more in our analysis section, to show how even simple changes in how an interpretation looks, right, can have big differences in terms of, like, let's say if a doctor is looking at these rules and trying to make some decisions and so on, the cognitive load that is incurred with small changes can actually be pretty big. Right? So while computationally we might be like, oh, that's a list, there is ordering, there's a set, there's no ordering, like that's the difference. But like these things have a lot of impact, and we'll talk about that a bit more later. So this approach will also hopefully make it clear to you as to what exactly is the desiderata behind these kinds of approaches that are being used to construct these rule-based models, again in a renewed fashion since 2015. So this is what is the set of criteria that this approach is focusing on, which is you want to account for recall, precision, distinctness of the rules, sparsity in the rules, and then covering all the classes, right? And recall and precision is important for accurate predictions, and distinctness, parsimony, and covering all the classes is important for interpretability, right? So just to go over some of the terms here, and just bear with me as we do this, because these are the building blocks of a lot of the things that we'll talk about later. So then we are going to just skim through these details and say, oh, we refer to them then, okay? All right. So the objective function in this case, as we were saying, it's trying to sort of encompass 5 different criteria, right? So parsimony, or the sparsity, is basically trying to ensure that there are fewer rules in the rule set. So now our goal is we have to pick from a candidate set of rules that we have. We need to pick a subset of some k if-then rules, and then that will become our classifier, right? And the first criterion in that is we favor fewer rules. So we want to either minimize the number of rules, which is denoted by size of R, or maximize the negative of that. So that's essentially what you see is that expression there. Okay? And also fewer predicates, which is basically the number of conditions in the rules, that should also be smaller. So we want to minimize that or maximize its sort of complement or its negative, right? Now, in terms of distinctness, because what we are looking at here is trying to find a set of if-then rules, we want to ensure that the points being covered by these set of rules is minimal, right? Or covered by multiple rules in this set of rules is minimal. Because otherwise you're essentially just creating duplicate rules, which you don't need, right? So you're trying to basically minimize 2 notions of overlap, which is intra-class overlap and inter-class overlap. So basically the point is that the number of points that satisfy more than one rule should be minimized. Okay, so that's what this expression is trying to capture. And then the next one is class coverage, which is you are basically checking to see that there is at least some rule corresponding to a given class or any given class C. So that minority classes, for example, in the kinds of data sets we are looking at, like the healthcare data sets, some rare cancers, they are like present in such tiny number of samples in the data that classifiers might often just ignore them because it doesn't matter to their overall accuracy. Right? But here we are sort of forcing that to happen, and we want every class to be represented in some rule. And then, of course, there is the precision piece where you're trying to minimize incorrect covers, right? So basically, we want to minimize for each rule that we pick in this set of rules, the number of points which satisfy the rule but do not belong to the class that the rule is assigning the point to, right? So that ensures precision, which is important for accuracy. And then recall, and the way we are sort of trying to enforce recall is that you encourage each point to be covered by at least one rule in the set that you produce. Right? So for example, that correct cover that you see there, that's basically capturing the number of data points which satisfy S, and also which is the rule S, and also belong to the class C. Right? So you're basically trying to ensure that no point is left out from this covering process. Okay? All right, so putting it all together, what you see is you can basically combine these, put it into an optimization problem. Essentially you'll get some kind of argmax problem like this, and then a summation over all these factors. So the property of this kind of an objective, or the set of properties of this kind of an objective, is that this turns out to be something that's called a non-normal, non-monotone, and submodular optimization problem. Okay, so without going into too much details, because that's not the point of this conversation, maximizing such a problem turns out to be NP hard, but the good news is there are some approaches which can provide reasonable approximations, and we can use those to efficiently solve this objective, right? In fact, faster than what the Bayesian rule list was trying to do. Okay, right. So with that, I think we are kind of pretty much covered like some of the key approaches that were proposed as the interest in rule lists and rule sets got rejuvenated somewhere around 2015. There are also several other classes of interpretable models. So next one is called as risk scores. So risk scores are basically things that look like this. So I'm going to just let you guys see this as I pause for a minute. So what you see here in these kinds of risk score lists is that for each condition, you're assigning points. For example, if the number of prior arrests is greater than or equal to 2, that's worth 1 point, right? And if your age at release is greater than or equal to 40, that's actually a negative 1 point. So you're trying to sort of create this kind of scores associated with conditions, and at the end of the day, you will just sum up all those scores, and the resulting score will tell you how risky it is, for example, for a defendant to be released, or how much of a risk there is in a person defaulting on a loan and things like that, right? So it's almost like saying if this condition holds, add a point. And as these conditions hold, keep adding points, what is the total, and that total will tell you how risky the person is, okay? So this kind of a construct is actually pretty popular both in medicine and criminal justice. Like I myself collaborate with doctors and folks in criminal justice, and they are very comfortable with this kind of risk scores, because all they have to do is just kind of go through that checklist and assign points, and then they get a risk score. So that's why they're pretty popular. In fact, the existing models of risk scores that are out there quite a bit in practice in domains like medicine and criminal justice are like handwritten or hand-drawn risk score checklists, which have been sort of made up by domain experts or doctors or lawyers and judges. Of course, they're using their domain expertise in coming up with those lists, but essentially they sort of prefer these kinds of checklists with scores quite a bit. So there's something that naturally comes to them in terms of utility. Okay, so how do we now construct these kinds of risk score checklists using data? Right, so that's the problem, or that's the question that was dealt with by Uston and Rudin in the year 2016. Okay, so this is roughly the kind of problem that they formulate. It turns out to be a pretty complicated problem to actually solve correctly, accurately. So we'll get to that a bit later. But essentially, if you see, what this is trying to do is that, so you're trying to basically formulate or come up with this kind of a set of conditions and corresponding scores such that you are basically minimizing two terms. So the first one is basically ensuring that your scores work out. So the scores that you're applying, and then you will sort of use those scores to then convert them into the probability of risk associated with someone, let's say, right? So the scoring mechanism, the first term will ensure that that scoring mechanism or the scores you're assigning to each of the the predicates in your risk score list actually map to the precise risk in practice or the real estimates of the risk in the data. So that's what that last term is doing in the objective. And then the second term, you are essentially trying to sort of minimize the number of the predicates or the terms that will get onto this risk score checklist, right? So you don't want the checklist to be, having like 100 attributes there, right? So you want to minimize that. So that's what that second term, which is a regularization term, is doing. And then of course there could be a bunch of other constraints on how you will pick these conditions that you see in the risk score checklist, and also the scores that you assign to them. For example, there might be a condition that don't assign continuous valued scores. The scores that you assign should be integers because those are more interpretable, right? So you can think of them as 1 point, 2 point, but not as 1.73 or something, right? So there could be a bunch of such constraints both on what features you're picking and also what scores you're assigning to them that is encoded by the condition there, right? So the above, when we put together some of the more sort of practical conditions into this problem setup, turns out to be a mixed integer program, and it is optimized in this particular work using a cutting plane method and a branch and bound technique. So it does not have an easy solution, but I think we'll leave it at that, okay? All right, so the next class of models is the generalized additive models. So this is the class of models which basically produces outputs like this. So what you're essentially seeing is that you kind of see what are called as shape functions associated with input variables. So what this is showing is demand is your outcome variable, okay? And each of the variables you see on the x-axis are your input features. So this is kind of showing how the outcome variable will change as a function of each of the input variables, right? So as R increases, what happens to demand? And as temperature increases, what happens to demand, and so on. And by the way, these are not just plots from the data. This is actually the output of the method that is generalized additive models. Okay, so it shows you how the output can be modeled as different functions of input variables. So the output in this case is essentially a summation of all the curves that you're seeing here. Okay, it's like an additive combination. So just to show you a precise mathematical form of this, so for example, the first row here is essentially like a linear regression model, right? So your y is basically this kind of a additive or like a linear combination of different features that you have. And then we go one step up to a generalized linear model where you can take a function of y and then model it as a linear combination of different input features, right? Then we can think of an additive model where your y will just be an additive combination but of different input, of different functions of the input variable, right? So each input variable, you can learn a separate function over it, and then the additive combination of that will give you y. Now a generalized version of that is basically a generalized additive model where you can take a function of the output variable, that is g of y, and then think of that or consider that to be this kind of an additive combination of input functions of different input variables. Okay, and of course if you want to make the model more complex, your y is basically just a function of all the input variables, and that could be an arbitrarily complex function, right? So think of deep neural nets and so on, which fall into the last category. So this table also kind of tries to summarize some of the knowledge that we have been thinking about. So if you think of a linear model, it's just a bunch of coefficients associated with each feature we multiply the feature by the coefficient, add everything up, we get the output, right? So the interpretability or the intelligibility factor is high. Accuracy may not always be high. Of course, depending on the data it might, but it may not be as high. Now, if you think of the generalized linear model, which is something like a logistic regression, in that case also, your intelligibility or ability to see 5 weights and then see what they're doing, that is good. But again, accuracy may not always be good, right? And then the third row is the additive model, where you are just thinking of additive combination of different functions. Your intelligibility is probably a bit worse off than just seeing, the actual variable itself, because now you're seeing a function. Your accuracy might improve a bit though, right? And the same is the case with generalized additive model. So you are seeing complex functions now, so your interpretability is probably not as high as just thinking of it as one variable and its weight, but at the same time it helps with accuracy a bit, right? Okay. So GAMs and GAM squares, I guess that's how they're called. So these have again become popular starting 2015, 2016. So GAMs are essentially what we just saw. So they sort of model these first order terms, and they're like additive combinations of the functions of the different input variables. GAM square is basically going one step further, and it is also considering pairwise interactions between features. Right? So the claim is that these kinds of shape functions that you saw earlier that are produced by these approaches are interpretable, and we'll talk about that as well in just a bit. Right? So how to learn these kinds of models? So the idea here is that given that you're trying to fit a function on each input variable and then do an additive combination of it, so you basically represent each feature or each component as a spline. And then you basically use a least squares formulation and then run an optimization procedure to sort of balance smoothness of the spline as well as the empirical error, right? So that's how you go about it. And then with GAM square, you also have the higher order interaction terms to consider. So in this case, you first build a GAM, which is without the interaction term, take the residual error, okay, and then rank all possible pairs of interactions in the residual, and basically try to pick some top k interaction pairs that are contributing to the residual using some sort of feature selection type approaches, and then like even cross validation, right? And then just pick those top k pairs and now try to again repeat this learning procedure where you're basically representing the pairwise interaction term as a spline, and you're just sort of using a least squares formulation to fit it. Okay? So yeah, if some of this feels a bit fuzzy, that's fine. These are details of how exactly people are trying to learn such models, but the important piece is the construct that you saw, which basically looks something like this. And the claim is these kinds of things are actually interpretable. I think I'll just sort of do a poll here to see how many of you think this is interpretable. Show of hands. Okay, that is some of you, all right. What about the rest? How many of you think it's not interpretable? Let me see if there are people who are undecided. Oh, there are some undecided folks. Okay, so why do you think it's not interpretable?
I think maybe if there are one or two features, I'm okay looking at these curves, but then like beyond 5, I think it's too much again.
Right. And what do you feel about thinking about this as the whole outcome variable is some kind of additive combination of all these shapes?
Right. So I think I understand the sensitivity to each variable, but not the combined effect of achievements across multiple dimensions.
Right. So I think the sort of intelligibility or the interpretability, I know we are using these terms somewhat loosely, but of GAMs has been debated quite a bit. So again, there are pieces of it that make it interpretable, which is you can kind of see how the output would vary as a function of individual input variables, right? But at the same time, thinking about all the variables in one shot or in conjunction and then thinking what their effect would be on the output is a little hard to fathom from something like this, right? So there have been debates about like whether this should be considered interpretable or not. In fact, I think, you know, there is a dearth of like doing more user studies to actually check if some of this is considered interpretable, if so, by what kinds of users and so on. Okay, all right. So with that, I'm going to keep us moving, and let's talk a little bit about prototype-based models. Okay, so first, from here on, we are actually also jumping into some more complex aspects, but I'm first going to describe a very simple approach for what would be a prototype-based models, and then we'll see how to sort of make deep learning models interpretable by incorporating, you know, prototypes or some other constructs. Okay, all right. So the goal with this particular, like the basic problem we are considering here, is to identify k prototypes or instances from a given data set, such that if there is a new instance, we can use these prototypes to assign labels for that instance. Right? So you want to pick some representative points in the data set such that if you give me a new data point, I should be able to compute the nearest neighbors among these representative points and assign the label of that nearest neighbor, and that should be the correct label for that new data point. So in some sense, I'm trying to build a classifier through these representative data points. Okay, is that clear? Right? So the way at least this paper goes about this problem is that you consider each instance to cover some epsilon neighborhood around it, right? Like an epsilon ball around it, we consider that each instance sort of covers that neighborhood, okay? Which means, and cover means if a point lies within that epsilon distance from any given instance, then you say this point belongs to the epsilon neighborhood of that instance. And I'll show you pictorially in just a little bit, right? So once you associate this kind of a neighborhood with each instance, now what you have done is you can sort of see the analogy between this and a rule, right? So earlier we were trying to come up with a subset of rules in the rule set that we discussed about, or the interpretable decision sets that we discussed about. We were coming up with a subset of rules that can cover all the points in the data and also be accurate classifiers, right? So similarly, we are just replacing the construct of the rule now with a prototype or an instance, and an instance is said to cover all the points within the epsilon ball neighborhood around that instance, right? So for example, and then once we see this sort of deduction or reduction to this problem we thought about earlier, as soon as you define this neighborhood, you can apply all the optimization problem that we talked about earlier in the context of rule sets, and then find a subset of prototypes that maximally cover the data, but is also accurately assigning labels to the points that are getting covered, right? So just to show some pictorial representation of this, and the value of this epsilon that defines the neighborhood can be given by an end user, right? So this is basically showing for different values of epsilon, if we pick certain prototypes, what are the neighborhoods that they're covering, right? So if epsilon is small, you'll end up picking a lot of prototypes because, you know, it's only covering a small portion of the data. Each prototype is only covering a small portion of the data. But as you increase the value of epsilon, you'll end up picking fewer prototypes because each prototype covers a larger chunk of the data, right? And then, so essentially what you have built is some kind of a nearest neighbor classifier, and you have sort of took some prototypes out for building such a classifier. All right, so this is another popular class, and this kind of nicely feeds into our discussion on, so far we have been talking about, you know, we want simpler models, simpler constructs, how do I learn rule lists and rule sets and, you know, GAMs and, you know, simple prototype-based models. So I'm sure some of you are wondering, okay, when will we get to deep learning, right? So all these seem like nice and simple models, but these are not going to help with my accuracy. I want to run deep learning models. So what about interpretability there, right? So here we are jumping into that territory. Okay, so this is basically, and there are few approaches which try to do something like this. The idea here is that you can make deep learning architectures interpretable by essentially introducing these kinds of layers, right? So there is a prototype layer followed by a fully connected layer. So you can augment these two layers almost towards the end of a given neural network architecture and try to get some interpretability in terms of the predictions being made. Okay, so this specific architecture that you're seeing, what it has is this first part is basically what is like a autoencoder, right? And then you take the output of the encoder and then you pass it to the prototype layer and the fully connected layer, and then you get the output. And we'll go into the details of what each layer is doing. Okay. So, so like let's say our input has the dimensionality of p, right? So it's all real numbers. So there's the vector of real numbers and of dimension p, and then that passes through the encoder, and then it gets transformed into RQ, which is basically a q-dimensional vector of real numbers, and q is typically less than p, right? So for those of you who are wondering what exactly this component is, think of it as essentially it's creating a low-dimensional representation of your input, right? So in some sense, you're trying to reduce the dimensions in your data while preserving the most important information, okay? So you're doing that in the first component, and then you are inputting a q-dimensional vector of real numbers to the prototype layer. And what is the prototype layer doing? The prototype layer is actually responsible for computing or learning the prototypes, and more specifically, each node in the prototype layer is computing this value, right? So for example, P1 is computing, so given an input data point X, we got this Z, which is the transformed version of X, and then each of those nodes in the prototype layer is computing the sort of this L2 norm difference, or you can think of it as the distance between Z and P1. Okay, so between the transformed input point and the prototype that it's learning or it has currently learned, right? So in some sense, each layer is just outputting the distance between the input point or some transformation of it and then the prototype chosen so far. Okay? All right. So now that that's the case, the dimensionality of that vector will be m. So that is basically you get one distance value with respect to each prototype, right? So you get, first node is computing the distance between Z and P1. Second node is computing the distance between Z and P2, and so on. You get one scalar value from each of those nodes. So the entire output of that layer will be m different values. Okay? All right. So then the fully connected layer is essentially computing a weighted sum of these distances, right? So you got the distances. Now you can make these distances the weighted combination of these distances using this fully connected layer here. And then, of course, so that will sort of take the dimensionality from Rm, and you're sort of multiplying that before with W. And so basically that will end up being a k-dimensional vector, and that in turn can be passed on to the softmax layer in order to output probabilities over k classes, right? So basically what you're doing in sort of all these details is that you're essentially trying to, so normally deep neural networks would basically have, let's say, this component, none of these two layers, and then you go straight there, right? But you're introducing a couple of interpretability layers there, or mainly the prototype layer there, so that for every instance, you also have a prototype that sort of says something like, oh, I made this prediction on this instance because it looks like this prototype. Does that make sense? So that's the thing that we are trying to get to here by adding these kinds of layers. Okay? All right. Okay, so think we have a little bit more time before the break, and I'm going to cover this as well. So the last is attention-based models. Again, this has gained a lot of popularity in recent times. So the idea is, just like we were thinking about adding these prototype layers to deep neural network architectures, here we are thinking of adding another kind of layer, which is called as attention layer, right? Okay. So just to illustrate this, let me first show you this example of a machine translation task, okay? So there is nothing interpretable here. We have not yet introduced anything, but this is an example of an architecture of a model that people use to do machine translation, okay? So the idea here is that, so there is your input. You are trying to translate this sentence from English to French, okay? So there are 3 tokens in your input, and each token is passed through an encoder, which will basically generate some kind of a hidden state representation for that token. Okay, so that's what this side is doing, right? And as you can see, the hidden state representation for the second token depends on that as well as, this input, right? So both are the inputs here. So in some sense, you're trying to basically take each word and then get some vector representation of that word through some process. Like, just think of it in that abstract way. Okay. So now once this encoder is sort of built, the next part is that there is a decoder on the other side, which is basically, so there is a context vector in between. I think for the purpose of this architecture, you could assume that C is basically just taking the value of H3, which is the encoded representation of the last word there, okay? So I think there are architectures which do use that and some functions of H3 and so on, but let's just assume C is H3, okay? And C is often referred to as the context vector because it is trying to capture some context about the input, okay? All right, so now the next set of layers that you have is the decoder, and that takes C as input and then tries to generate a hidden state representation for each of the output words. And then, once you generate that hidden state representation for, say, the first word in the output, then conditioned on that hidden state representation, you can generate the actual word, right? So that's how machine translation happens with models like these, okay? So now, attention layers, how to add it in this kind of an architecture, right? So before I describe exactly what is attention here, the change that you hopefully noticed from the previous slide to this one is that we kind of added some complexity to the context vector, right? So what we are doing is now the encoder has remained the same, the decoder has remained the same, the context vector is no longer just C, so we now have like separate context vectors corresponding to each token of the output, right? So the way we introduce interpretability into this is as follows. Okay? So the context vector corresponding to each hidden representation of an output token, which is SI is basically the hidden representation of the output token I. So the context vector will be modeled as this kind of a combination, which is Aij and then Hj, right? So in some sense, what you're doing is you're representing each context vector as some kind of a combination of each of the hidden representations from the encoder side. So you're no longer saying, I'm just going to take H3 and then all the decoder pieces will depend on just H3. What you're saying is, my context will be some combination of these 3, and I will learn what that combination is, and that combination will tell me the importance of each of the input words in generating each of the output words, right? So that's exactly what you're doing when you basically add this kind of a term there, okay? So in some sense, the Aij that we have introduced there, it captures the attention placed on input token J when determining the decoder hidden state Si, right? So in some sense, how much does the output word I depend on each of the input words j, that's what is captured by aij, right? And that is basically the notion of attention weights, and that basically describes the importance of each of the input features in these kinds of networks.